Hello, I'm Robert, and I'm the author of Touch Mars, which is a book about planetary protection. It's about 1,000 pages, and as far as I know, it's the first book that's an entire book on the subject. It's free to read online, so I've got a long-term interest in this, and I've read up a lot and talked to people and so on. And I was very concerned to hear about NASA's recent announcement, or their report that was presented to NASA, and studies articles saying that they're actually considering adopting these recommendations. So the report recommended that NASA should reconsider how much of the Mars surface and subsurface could be Category 2 instead of 4. Now this change from Category 2 to Category 4 would mean that human beings can go and land on Mars without taking any precautions, just to document what they're doing, just as they do on the Moon. And it would mean that we can return a sample from these areas of Mars back to Earth without again taking any precautions at all. Just assume that it's safe. They're defining it in such a way as to define Mars as being safe for Earth life, and Earth being safe for return samples from Mars. And the basis for this, they say various scientific studies to support this, 4, 5, 6 and 7. If you go and look at them, then the first one is 1983, then 2008, 1969 and 1984. And then the very first one has a 2014 study, which is the most recent they have. But there's been huge changes even since 2014, since our understanding of the habitability of Mars. And there's been a long debate in the Astrobiology Journal between astrobiologists of the two sides, which was not resolved with a consensus, in which some were saying that we should reduce the planetary protection requirements for Mars, and others saying that we should continue with them as they are now. And so this is only presenting one side. It's presenting the side of the astrobiologists who say that we should stop trying to protect Mars. And in this study, it was not this, and both sides of the debate in the Astrobiology Journal, they did not agree with this idea that there's no longer a chance for terrestrial organisms to spread on Mars. Both sides assume that if you landed human beings on Mars, then it's pretty certain that they would. There's not certain. There are astrobiologists who think that Mars may be sterile, but it is a significant possibility that some of the new habitats that we find there, that Earth life would be able to propagate into them. And then, if that is true, then after human landing there, it would be irreversible. There would be no way of returning it back to the situation it is now without any Earth life from present-day Earth. And this could be catastrophic for the possibility of finding out new things about Mars. And to give an example of exactly how vulnerable Mars life could be, we don't know, we have no idea. There have been no life detection instruments sent to Mars since the 1970s, and those were very basic by modern standards, although they were, of course, the leading technology of their day. And the Mars meteorite, that there was so much fuss about them, was eventually decided that we do not know if there's life in it or not, and so the conclusion in most people is that they didn't find life in this Mars meteorite, but the structures in it that could potentially be fossils of ancient life on Mars were far too small for Earth, the smallest Earth cells, and this suggests that they could be an early form of life, which would be maybe RNA life, or whatever it was that came before DNA. And if you go back then the life back then could be very vulnerable to modern Earth life. For instance, very early life may well have not been differentiated into different species of microbes. One of the main hypotheses for before the last universal common ancestor is that this life may have swapped genes very readily, and that there were different cells that are different mixes of the genes, but they could all swap genes with any of the others. And you can imagine life like that, which has just got no defences. There's competition between genes, but no competition between the microbes. And imagine putting an Earth microbe into a habitat that is colonised by life like that. And there isn't going to be much left, is there? And we can be pretty sure of that also, because none of that life survives on Earth now, today. Although there have been many searches and we have some possibilities of a separate shadow biosphere, it hasn't been discovered. But there must have been earlier much simpler life on Earth than what we have today. It's absolutely impossible that the complexity of modern life arose without something simpler first. And that could be on Mars. And this would be an amazing discovery, and there's no way we can make it happen in the laboratory. We can't create life. We can only take life and modify it. We can't create even the simplest cell from basic chemicals. We just don't know how to do that. So we really are dealing with a situation where Mars life could be of extraordinary interest and very vulnerable. So that's for the forward direction. And then in a backward direction from Mars to Earth, then you get many people saying, oh, it has to be safe, there's no reason why Mars life could harm us. But if you go back to, if I look up Joshua in my own book, I'll look up Joshua Lederberg, who was Nobel Prize winning microbiologist and microgeneticist. And this is what he says there. If Martian microorganisms ever make it here, will they be totally mystified and defeated by terrestrial metabolism, perhaps even before they challenge immune defences, or will they have a field day in light of our own total naivety? And then he has another longer quote, and says that you could argue that they can't cause any serious problems because there's been no biological contact. On the other hand, you could equally well argue that that terrestrial organisms evolved no defences for exactly the same reason. And it's possible that it's also possible that life has been exchanged from Earth to Mars, but we don't know this. The last chance for that to happen was 66 million years ago, at the time of the Chicxulub impact, which did send material as far as Mars. But it's not at all certain that any Earth life got there on that impact. It hit into a shallow tropical ocean, which is not the most likely place to find Earth life that could survive on Mars. Then the shock of impact has just sent it exiting the Earth's atmosphere at 11 kilometers per second, which means it has to leave Earth's surface even faster than that. And there's a huge instant shock, which is much harder than quite hard for even microbes to withstand. It's not clear that many of our microbes, if any, would actually survive the shock of the impact and head off into space. Then it would be the rocks are flying through the atmosphere at faster than the fireballs. When you see a fireball, like they get as bright as the moon because the fireball breaks up and burns up on the entry to the Earth's atmosphere. This is talking about exiting the Earth's atmosphere faster than that, creating a huge fiery fireball that would certainly burn all life around the exterior of this meteorite, and it would go in through cracks in little plasma jets and sterilize it right interior. And there might be some life that would survive right in the interior of one of these rocks. But it's not clear and then it has to go it has to go through space for at least decades, probably a century, before the earliest rocks start arriving on Mars. And when they get to Mars, then maybe deep inside the biggest rocks, there might be some life that has survived all this. But then it lands on a surface where there's no standing water. There's no seas. The soil isn't moist. The soil is very dry, and there are possibility of these brines in here and there on soils. But remember, it's stuck inside this rock. And is this life going to get out and into these habitats? So it's not at all clear that any life from Earth has even got here, even all the way back until perhaps the times when there were lakes and seas on Mars. Then there was a better chance of life being transferred from Earth to Mars. And then very far back when there were seas on Mars, there would be quite a good chance, if it was to withstand the shock of ejection and the vacuum of space and all that. But then how hardy was this very early Earth life? Was it able to transfer to Mars? Astrobiologists do not know if any Earth life has been transferred to Mars. And when they design life detection instruments for Mars, then they do this based on, they make no assumptions. They're not able to assume whether it's related to Earth life or different biochemistry. Both are possible. So, and you will hear space advocates just saying, oh, we know that Earth life is on Mars and it's exactly the same as on Earth. We don't know that. And then the other direction, from Mars to Earth, then we don't even know what the Mars life capabilities are. Maybe it's completely damaged by even the slightest shock, because that's not a natural thing to happen to life. We just don't know. Especially if it was some kind of early life, like I was just describing. And it is possible that Earth life originated on Mars, but if it did, then it doesn't mean that all the Mars life ever got to Earth. There could be, we have several different genuses of life, or distinct groups of microbes on Earth. Now, it's entirely possible that Mars had more groups than we have on Earth, and that only a few of them were hardy enough to get through from Mars to Earth, and the other ones might still survive on Mars, and they could easily be vulnerable for the more evolved life that is on Earth. There's lots of ways that you can look at this, where, and of course, if Mars life is this very early vulnerable life, it wouldn't have got here, or if it did, it would have just been gobbled up. So we can't know that Earth life is safe for Mars, or Mars life is safe for Earth. Now, so I'm going to talk about this some more later on, but first of all, one of NASA's main reasons for wanting to classify Mars as being safe is to be able to return a sample from Mars to Earth. Their mission in 2020 is going to go to Mars and cache samples which they want to return to Earth. And if they can categorize Mars as being Category 2, then according to the Outer Space Treaty, that would mean that there's no problem returning samples from Mars to Earth, because you've defined it as being safe, and so there's no risk of there being any life in it. However, this is not based on science. As I said, there's been this ongoing discussion in the Astrobiology Journal about this, and it's not at all clear that Mars is sterile. In fact, there's lots of reasons for thinking it probably isn't. And to give an example, which applies in the equatorial region, then Curiosity, where it is driving over the sands, it discovered that there's a level of humidity which is quite unexpected in the air as it drove over the sands, which varied during the day. And looking at this carefully, they found evidence that there must be salts, probably perchlorates and other forms of salts, but perchlorates are very common on Mars, and they take up water very easily, much more easily than on Earth. The Mars atmosphere at night has a very high level of humidity, close to 100%. That's because it gets so cold. There's a huge difference. It can get cold at night on Mars, so cold that carbon dioxide freezes out as carbon dioxide snow. That's how cold it can get, even in the equatorial areas, even in the warmest regions of Mars. And so, especially in winter, and when it gets cold, then the salts take up a lot of water from the high humidity of the atmosphere, because, like on a warm day, your clothes dry. It's the same on Mars. When it's warm, the air is very dry. When it's cold, then it's very moist. And it gets close to 100% humidity, and then salts take up this humidity and become liquid. They become a salty brine. Then in the day, as it warms up, and this is just a couple of centimeters below the surface, very close to the surface, so it's warmed up in the daytime, and then the salts evaporates this liquid. And these conditions are so extremely cold at night that they don't think Earth life would be able to survive at night, even though it's quite liquid. In the daytime, then it would be too salty for Earth life. So it's probably not conditions in which Earth life could live, but it could be conditions in which Mars life could live, because Mars life would be used to the perchlorates, just as our life has ordinary salt in it, because we're evolved on a planet with lots of salty water. Well, on Mars, the natural salt to use there would be perchlorates, which is a much the salty brines with perchlorates, so liquid at much colder temperatures. They prevent freezing crystals. They are good antifreezes, and then it would also quite likely have hydrogen peroxide in it. And so the life on Mars, there could very well be life that incorporates at least some element of this, especially since it has these very cold brines anyway, which we don't have on Earth. So any life that could survive in them would be highly evolved to be able to adapt in them. So if there was a mix of different life and some could survive at cold temperatures, then it would evolve and it would be there. So there is a not inconsiderable chance that these salty vines do have Martian life in them. And this Martian life could form biofilms on Mars, just as it does on Earth. And this life would incorporate the water in it. So then all these calculations about how in the daytime the salts are going to evaporate and it'll just be far too salty for Earth life, it's not going to apply anymore if you've got life there, because the biofilm would capture the water at night and keep it during the day, and it would actually metabolize more in the warm conditions in daytime. So there's absolutely no guarantee that there's no Martian life, even where Curiosity is driving right now, and there's no guarantee that Earth life is unable to survive in these biofilms. You can't prove a thing like that because we have never sent any life detection instruments to Mars since Viking in the 1970s. In the 1970s, they were rather crude instruments by modern standards. They heated up looking for organics in little ovens. That's much like they do with Curiosity today. But the problem with that is that there are perchlorates in the Martian soil as well, and the perchlorates react with organics. And when you heat them up in these ovens, then you destroy all the organics with the perchlorates. So if you've got only a small amount of organics, such as a few spores in the dust, you're just going to destroy them when you try and examine them with these little ovens. And then the other way that they can do it is that they can look for the life by trying to reproduce it in a medium. And the Viking labelled release did get a signal. It's the only one of the three signals with the three experiments that got a pretty definitive signal. It was very puzzling, but remember, it had these surprising perchlorates which nobody expected, which interfered with experiments in unexpected ways. And a later reanalysis of the Viking labelled release, which the way it worked, it took up radioactive carbon from some food that was given to it, and then if it metabolized, then it would have given off carbon dioxide where you could detect the radioactivity, and so decide from that whether or not it was being metabolized. I did get this signal, but it was confusing. It didn't quite work as expected, and the other ones seemed to be contradicting it. And so at the time, the conclusion was it's sterile, but we no longer know that it's sterile now, because of these new discoveries about Mars, and because of looking back at this experiment. They actually found a circadian rhythm. A specialist in circadian rhythms looked at this experiment, and he found that a signal which was out of phase, I can't remember, I think it was half an hour or something like that. Again, it'll be in this page in my book on circadian rhythm. I can find it in a minute. Yes, here we are. And he found the circadian rhythms, there they are. But his circadian rhythms were out of phase. It could have just been due to the warming, but see if I can find the number. So he found, yeah, here we are, here's the phase thing. They were delayed by 2 hours. Now you can have, so the temperature is fluctuating because of the variation of the day and night on Mars. But the rhythms from the labeled release, the releases were out of phase with the the temperatures. And that's very hard to explain with simple chemistry. So because of this and various other things, then some astrobiologists are coming around to the conclusion that it is possible that Viking did detect life back then. And if it did, we haven't sent anything to Mars since then that has the capability to detect life in these small quantities, especially since Viking also dug below the surface to get its sample. And that would get into this. For instance, this 2 centimetre below layer, it could have dug up some of this Martian life and put it into its sample, into its experiment. And Curiosity can't even dig down 2 centimetres. So although it has indirect evidence of this life, it has no proof that it has indirect evidence of these brines. It hasn't proved they exist, and it can't dig down and study them, because it hasn't got any digging implements. It's got a little drill, but it can only drill into rocks a little way. It can't dig 2 centimeters into the dust. And so there's it's certainly possible that there's life even where curiosity is. There are many other ways. The DHL in Germany, which is like the equivalent of NASA or ESA, and they found that they were able to get lichens. Again, I can maybe look at, if I look up lichens on here, I'll find the DLL experiment. Here we are. It's lichens and cyanobacteria. So there's their experiment. And you can see they're testing a little rock with some lichen on it on Mars. And there it is. And this is a chlorophanem, which is it's a lichen which is able to metabolize under high UV conditions very high up in Antarctic mountains, which is pretty close, as close as you can get to Mars conditions. And they were surprised to find that it actually continues to metabolize and continues to grow and photosynthesize. And the remarkable thing is that as lichen has got a fungal and an algal component, and the fungal component was able to continue to grow, presumably getting its oxygen from the algae, because there was no oxygen to speak of in the atmosphere that they provided for it, simulating Mars life. And it was actually growing, and it's only a short experiment, only a couple of months or so, I can't remember, but they came to the conclusion, and they also did experiments like that with blue-green algae as well, cyanobacteria. And these also were able to survive in Mars conditions, in the near vacuum, in the ultraviolet. And the interesting thing here is that in the Mars experiment, it was not using any water. It wasn't surprised, even with these salty brines. It was just using the moisture in the atmosphere. Like I said, it gets 100%, close to 100% humidity at night. And in Antarctica, then lichens are able to survive without any water by taking in moisture from the atmosphere. These same lichens are able to do the same trick in Martian conditions. So it's possible that there could be higher life forms like lichens on Mars. I'm not going to expect to find animals or insects or birds or anything like that, but you could have lichens and very likely to have microbes. And these could survive anywhere on the Mars surface. And the ultraviolet light, people often go on about how the ultraviolet light is sterilizing. What they forget is ultraviolet light is just light. And it can be blocked by a millimetre or so of dust. It can be blocked just by being in the shadow of a rock. And with this experiment, you can have partial shade. You have a crack or something with some lichen in it. So this lichen in the Antarctic mountains, then it has a kind of habitat inside. I don't know if I've got a picture of it, or at least the experiment. Anyway, I'm not sure I've got a picture of this, but in Antarctica, in my book, I probably have, take a while to find it. This actually also is a very widespread on Earth, and it actually survives in Mediterranean areas as well, where it's got a kind of flat habit where it just spreads out. But in the Antarctica, in the high mountains, then it's got a kind of, it gets into cracks in rocks, and it hides from the ultraviolet light. And it would do the same on Mars. So it's possible that this lichen, if transferred to Mars, might be able to survive there, clustering around in cracks in the rock and hiding from the direct sunlight and getting partial indirect light. It's got various pigments in it that help to protect it from UV light. So there are many ways that life could survive on Mars. And so if they return now, if NASA goes ahead with this and they redefine parts of Mars as Category 2, this will not solve their problems with returning a sample from Mars back to Earth. The reason is that it does solve it for the Outer Space Treaty. The Outer Space Treaty has very little on this subject. It's just a few sentences on harmful contamination, and then everything since then is people attempting to do legal interpretations and spinning a lot of stuff out of this little phrase, harmful contamination. What did the framers of the Outer Space Treaty mean by harmful? and it's been taken to mean harmful to experiments of other parties to the treaty. If you send an experiment to Mars and messes things up for other people, then that is harmful for their scientific experiments. It may have a wider meaning, but that's part of it. And the same way coming back from Mars to Earth. So what they're doing, if they recategorize and then these categories 1, 2, 3, 4, and 5, they were done as a result of the entire legal foundation of all that is just this little phrase about harmful contamination in outer space treaties. So it is very weak legal foundation, and so it's really based an awful lot on countries also mutually agreeing that it's important to protect Mars and to protect Earth, and together with the Outer Space Treaty and this combined interpretation of them all, that this is how we understand it, and the meeting of COSPAR. So it's an awful lot based on that. But legal, there are various legal opinions about what the legal situation is there. There's one lawyer who tries to interpret it in a much laxer way, and hoping that that would make it easier to return things for humans to go to Mars. So there's legal contention about the Outer Space Treaty. This lawyer is in a very much minority, and most lawyers say that they're wrong. But whatever the situation, the Outer Space Treaty is not a very waterproof, bulletproof, very strong agreement. But the thing is, if you return materials from Mars, it just wasn't written with this as the main aim. Well, it is one of the clauses, and it's passed off very quickly. But if you return a sample from Mars back to Earth, then you also encounter all the environmental laws to protect Earth. And those didn't exist at the time of Apollo. And the people who think about the Mars sample return, they just don't seem to have even started to think about these laws. Margaret Race, who's astrobiologist for SETI, she looked into it. And she worked out a whole sequence of different laws. I've got an article about it in which I tried to, she didn't give a time scale, and I tried to work out how long it would take to pass all these laws. And there's a sequence of them. They can't be passed all at once. Some of them have to be passed before other ones. And then once that is all done, then you have to start building your Mars receiving facility to return the sample. And you have to, before you can build your facility, now you could start building your facility straight away. You could start building your facility today. But NASA has a what do you call it? It's well, the way they do things. I'm sorry, words skipping my mind for the moment. But the way that NASA does things, its protocol, its procedure, is that it doesn't build things and doesn't do missions unless the legal provisions for it have already been passed, which is natural enough. So NASA would not build the Mars receiving facility until all the laws that have passed in order to make it happen. The reason being, because the law could be passed, it would mean that they have to build something different from what they started building now. So they can't start building this facility yet. And then when they start building the facility, they would have to test it, and this is because back in the time of Apollo, there were many mistakes made with the Apollo materials returned to Earth. The way they contained them was absolutely laughably no use at all, according to modern understanding of microbiology. And the way they did it was also would be totally illegal now. They published their requirements for the sample return on the day that Apollo 11 launched to Mars, launched to the Moon. And so nobody was given any chance to look at it and check it. And those were the requirements they actually used when they returned the sample from the Moon to Earth. And then even the astronauts got out of the return module in the open sea into a dinghy. And they talked about how the interior was covered in dust and they smelt it like gunpowder and everything. There's absolutely no doubt that some dust from the Moon got into the sea when the Apollo astronauts got out of their capsule. And so there really was no protection of the Earth from the Moon. It was all just show after that. Because there's no doubt at all that if there had been any life on the Moon, spores in the dust or anything like that, it would have got into the sea with Apollo 11. And the original plan was to lift the capsule all in one go up onto the waiting ship. But the crane, there was some problem with the crane, and so they couldn't do that very easily, and they couldn't wait to get it fixed. So they just sent the helicopter out and the people with the divers and the dinghies, and they just opened the door, and they handed in the decontamination suits for the poor astronauts to put on. And then they came out. The suits could have had dust on them, and the dust would have come out when they opened the door to the capsule. There's no way that protected her. And then there were many breaches after that with the sample return facilities, when people took things out of the sample return. And there's even a rather amusing story, Buzz Aldrin, and he talks about when they were in a quarantine chamber, and he says some ants came into it from outside, and he remembered looking at the ants and thinking, what is all this quarantine doing to, we've got ants kind of crawling in and out of our quarantine chamber. And so he's got a rather amusing story about that in his autobiography. So it was, and then there was no particular reason for a 2-week quarantine period either. That wasn't decided on any basis of any science. And for instance, some diseases have quarantine periods of 20 years or more. It's really difficult to contain anything with quarantine period if you don't know what it is. You can if you do know what it is. I mean, rabies has a quarantine period. I think it's several months that they do them for nowadays. It's not just weeks. I can't remember. I'd have to look that up. But you couldn't just take a dog into a country where there's protection from rabies in just 2 weeks, and yet they did that with the astronauts from Apollo. So really, that would just not be permitted today. You couldn't do it. We simply are not that lax now, like we were back in the 1960s when I was a child. And there's no way that NASA is going to be permitted to do anything like that with its sample return from Mars. And not because of the Outer Space Treaty, but because of numerous laws to protect the Earth's environment and our biosphere and our ecosystem. So do not worry. If you're scared about such things, do not worry. If there is a risk from Mars, then it will be thoroughly gone through in public consultation, and the public. Margaret Race found that the public will have a major part to play in this consultation, and they will have to consult us and talk to us. And it will not just be the Mars colonization advocates that are saying that do this. There will be people, everyone will be concerned, will be involved in it, and they will call expert witnesses, the astrobiologists. And the people, like in this debate in Astrobiology Journal, both sides of that debate will be involved, not just the ones that say it's safe. Because it's a proper legal procedure, and we now realise that the environment can be damaged quite often in unintended ways, and you have to look at these things carefully. And there are actually, so Joshua Lederberg, in that I gave that quote from him, saying how we do not know if we had Mars life came back to Earth, then it is entirely possible that there would be no defences against it. That is one of the two possibilities. And there are other ways it could be harmful. So imagine it was related to Earth life, and it is photosynthetic life, and that it has a 1% advantage over Earth life in its photosynthesis. And that is easily possible. So on Earth life, for some extrinsic reason, we have the purple salt-loving algae, which only use the red and the blue light, and then we have our plants and the green algae, which use green light. And the reason they use the green light may be because they evolved below layers of the red-blue light, and the red and blue light was filtered out, so they were left with the green. And the various other ideas, nobody really quite knows, or maybe they do now. Last I checked, it wasn't clear why Earth life uses green and rejects the red and the blue. So, so that's the. Another one of my senior moments, as it were. suppose that we have seaweeds that are dark brown because they live in the very dark conditions below the seabed, and they have antenna pigments that collect all the red and blue light, and they then transfer the energy so that it could be used in photosynthesis. Now suppose the perfect form of life would be black. So suppose that Mars life is black. Remember that it has half the light levels of Earth life, and of Earth, and so there'd be a lot of premium on being able to use very low light levels. Then you have the dust storms, which completely make it very dark for sometimes weeks on end. So it'd be high premium on life is very efficient at photosynthesis. So suppose that we get some life from Mars that is just a spore that gets into a spacecraft that's shuttled back from Mars to Earth. And this could happen even before humans get there. It could just be Elon Musk's starshot. He goes over to Mars in order to set up a habitat for the humans, and then it comes back to Earth. It can't be sterilized. It's a huge, big thing. If he gets this thing working, there's no way that he can sterilize the whole thing of Mars life. If a little bit of dust gets into it, then it could get into our oceans. And it gets into our oceans, if there's photosynthetic life in there of some sort, then suppose it's just 1% more efficient than Earth life, then it could eventually take over from all the Earth phytoplankton, and it could then be, and suppose it's then poisonous. For instance, its metabolism is based on perchlorates, and Earth life is not going to like perchlorates very much. And there could be lots of unintended poisons. There's no reason for life to be actually intended poisons. For instance, some of our green algae, they in the Great Lakes, and they poison cows and dogs. They damage their livers, and there's no advantage for them to do that. It's just that they've evolved to attack microorganisms, and these defense mechanisms are killing cows and dogs. So there's absolutely no reason why Mars life couldn't be poisonous to us. It could be completely harmless, but it could easily be poisonous. And there are basically three possibilities. It could be that Martian life is very feeble, like I was talking about, where it's early life, and then Earth life just goes there and it just rampages all over the place and doesn't even notice the Mars life. It could be the other way around. It could be that. So now, if you look at the Mars evolution, it had very great conditions very early on for life, but then within a few 100 million years, then it was much more difficult, and then you had these occasional lakes. You could argue from that, and then it was very, very difficult for billions of years. You could argue from that life on Mars is likely to have not evolved very far and still be very early life. And that would then argue in favour of that Earth life just rampages all over the Mars life. It could be the other way around though, because if you look at the early Mars life, then there were huge fluctuations in the habitat there. It had a very elongated orbit. It's hard to know how it got so warm, and it may well be that the oceans were freezing in winter and liquid and quite warm in the summer, and there were these huge changes in climate, far greater than we have on Earth. And sometimes the orbit's more elongated, sometimes it's less. The atmosphere got thinner and thinner and thinner, and then all these stresses may have accelerated evolution. There's no reason to say that it's less evolved. It could be more evolved as well. That's another way around. I mean, if you take the Mars meteorite, it suggests it's less evolved. But if you just use logical reasoning, I don't think there's any real reason why it has to be particularly less evolved. It could be more evolved. And so, is it possible that Mars life has developed capabilities that Earth life doesn't have yet, and that it would come rampaging over Earth life? And then, perhaps the most general case is that Mars life and Earth life, and this is what I'm writing on a paper that I hope to get published at some point, but I'm very, very difficult to find time to finish it. But I was encouraged by an astrobiologist, a professional astrobiologist, to write this paper. It's called Planetary Protection Measures Need to Take Account of the Potential for Severe Outcomes of Biosphere Collisions Based on Differing Biochemistries. And so some of these ideas that I'm talking about come from this paper. It's not peer reviewed, but it's I've talked it over, and I think it is very strongly cited, and I've looked very carefully at this. So I think it's worth consideration. And then examples. A lot of what I'm saying, like the examples of the cows, for instance, that comes from an astrobiologist talking about the problem of Mars sample return. But this particular idea of the photosynthesis could be more efficient on Mars, that comes from that paper. It's just an idea to look into there. And but then there's another one. There's a physicist called Grossman. He was interested in seeding Earth life on the dying on very short-lived biospheres around other planets, other stars, very short-lived stars, which have, but short-lived could mean millions of years. And he thought, what about sending Earth life over there? You don't want to send Earth life to a planet that has advanced life already, for the reason that Earth life might just like sending it to Mars, it might well destroy the life there. You might even have higher life there that is damaged by Earth life because it can't hit in some way. So you wouldn't want to do that. But he looked at the possibility of seeding these planets with a very short lifespan, or very short. The stars have very short evolution, and just for a few million years, and seeding it with Earth life. Anyway, he looked at the possibility of what happens if you mix two biospheres. And he came to the conclusion that the general case was that you have a mix of microbes of both sides that are equal, that are able to compete with each other equally. So then everywhere you just have all the microbial habitats, or many of microbial habitats, would have equal numbers of both. Now, in that situation, he didn't think that much would survive by way of higher life forms, because they're so dependent on microbes. And so you could easily end up, he describes it as being like a microbial mush, with maybe some very rapidly evolving, but the thing is, higher life forms are also very slow evolving, whereas microbes are rapidly evolving. And they would find it very difficult to survive based on this mix of all the microbial collections being a mix of these two different biochemistries. Like, for instance, in your stomach, if half of the microbes in your stomach are salt-based and half are perchlorate-based, and half are producing strange biochemicals that make a lot of sense on Mars, but Earth life can't make much sense of it, are you still going to be okay? Are you just going to get a stomachache, or are you just going to die? And if you have if you talk about the Mars life again, people say things like that Mars life could not harm us, could not be a disease for us. If you take the example of Legionnaire's disease is a disease of biofilms. It's not a disease of humans. It's not adapted to humans particularly, and it uses the same mechanisms it used to be a disease of biofilms. Sees our lungs basically as a nice warm biofilm, and then just goes and tries to eat it just like it does with a normal. A biofilm is a mix of microbes that work together, often different species working together, and they're often in a thin film over a rock or something, and they collaborate together. They often have interesting things like chemical signaling between each other, where it's a collaborative community of microbes. And this could very well be microbial biofilms on Mars. And these microbial biofilms may well have diseases. And those diseases might well then, like other microbes that are not collaborating and actually kind of harmful to the biofilm, and these diseases could then attack it's like a biofilm, the lining of our lungs. And if that happened, it could be that your Mars astronauts, they land on Mars, they get out, they're very excited, they dig in the sand, they discover this biofilm in just 2 centimeters below the surface, and then some of it comes back into their habitat because it's almost impossible to totally sterilize. And then within a day or two, they start coughing, and their lungs have been colonized by a disease of Martian biofilms. And there would be no use in using antibiotics. It's very unlikely that Earth antibiotics would do anything for Mars life. It's based on different biochemistry. And even if it's the same, it's quite likely it's evolved differently enough, because antibiotics, after all, antibiotics don't kill you. Antibiotics are very carefully designed so that they attack the microbes that attack us, and they're specifically designed to particular things in the way that the microbes work, and details of their cell functioning and other parts of the life of the microbe. So an antibiotic is it's remarkable that we can kill diseases without killing ourselves. With using these antibiotics, it wasn't until the antibiotics were discovered by Fleming and the whole history of it, it wasn't even known that such a thing existed, a way of killing diseases without killing us. So there's no way that we can prepare in advance to have any kind of medicine that we know would help protect our astronauts from Martian life if it happens to be dangerous. And astrobiologists often say, they do not think that life returned from Mars is going to be dangerous, but they don't go into any detailed arguments like this. And Joshua Lederberg, he was very clear that he didn't know that it would be safe to return life from another planet to Earth. And if you think about it like this and compare it with Legionnaire's disease, then imagine Legionnaire's disease that we had no protection for, and our lungs mightn't even know that they need to fight against it. They mightn't even recognize the signals from it that say it's life, because it's Martian life, different biochemistry. It just mightn't look like life to our defense systems, and the thing is, this is based on the assumption that our bodies produce defense systems, and Grossman he gave that as a reasoning, that they produce defenses only to fight against challenges that they have actually faced, and that you do not have defenses against hypothetical things that could harm your body, that your body has never faced, and that no human being has ever faced, and that no Earth life has ever faced in the entire history of Earth life. And it seems reasonable to suppose that our defense systems are not evolved to defense against all hypothetical attacks, but only the ones that are Earth-based, that previous human beings and previous life forms on Earth have already encountered. If that is true, then it is very unlikely that they would defend against a hypothetical attack from a Mars life based on different biochemistry. And that is basically what he was talking about, why it would be mystified. It is also possible that the Mars life just doesn't notice, is baffled by our chemistry. But basically, if it sees our lungs as just being organics, nice warm organics, it doesn't seem to be a very strong reason for supposing that Mars life would be baffled by it. It seems rather weaker that direction than the idea that Earth's defense systems would be baffled by Mars life. So there's entirely possible that we just can't rule this out. If there is life on Mars and it is independently evolved, I don't think it's at all certain that it is safe for Earth life or for our astronauts, until we only know if we study it. Now, if we can study it, if we can send life detection instruments to Mars, and that is what astrobiologists have argued for years and years. You go and look, just about all the papers on astrobiologists are saying what we have to do is to send life detection instruments to Mars to study it in situ. And we must have well-sterilized instruments as well, and go and look at life in situ on Mars and find out what it is. And especially today, we have wonderfully compact, tiny instruments that we can send to Mars. And we can even send genetic sequences to Mars. We can, which could be configured to sequence an alien biology as well, if we knew what the building blocks are. And we can certainly, if it's just a minor change, and we could design ones to sequence alien biology and send that to Mars as well. Once we know what it's based off, it's not impossible, and depending on how similar it is. And then the interesting thing is, if you send a genetic sequencer to Mars and you find that there isn't life, that there isn't any Earth-based life there, but you spot life in a microscope moving around in water, or you get it reproducing and actually doing something, then you know there's life there. You know it's not Earth-based, and that would prove it's got different biochemistry. And so it's entirely possible that and the many instruments we now have that are very, very sensitive. We have instruments that can detect a single amino acid. They couldn't have done that with Viking. We can now do that today. We could send an instrument that could pick up a gram of soil, sift through it, and find a single amino acid in it after dissolving it. And that's the astrobionibbler is an example of such an instrument. We have polyclonal antibodies-based instruments we can send to Mars. We have a wide variety of supremely sensitive instruments that we can send to Mars that are nothing like far, far advanced over Viking. But so far we haven't sent them. You can understand why. It's a big risk. If you send a life detection instrument to Mars and there's no life there, then it's just going to draw a blank. And I know it is of course extremely interesting and important that a zero result is very important in science, but it's hard to explain to your sponsors and to the general public that you sent a whole suite of instruments to Mars and they didn't detect anything of any interest. That seems like it's a waste of money. It isn't, but it's hard to sell. So it's not too surprising that it's been difficult to send instruments to Mars. I don't think there's any conspiracy. I think it's partly that. I think it's partly because the people who make the decisions are very focused on the chemistry and the biochem rather than the actual searching for life. But if we're serious about this, we do have to send life detection instruments to Mars. We can also send, we have wonderful microscopes nowadays, short field microscopes that can look well below the optical resolution. We can send those to Mars. We have holographic microscopes that can look at a sample in 3D, and you analyze it and you focus on the sample back on Earth. You take a holographic image on Mars, and you don't know where the life is in that sample. It could be anywhere. It could be very close or very far away. And you stream the whole thing back to Earth, and then you do the focusing on Earth. There are all sorts of wonderful, marvellous discoveries that they've made that we can now use to send instruments to Mars and detect life there in ways that we could never have done before. And then people worry about this, and they say that but we've got to send humans into space. Now, to start with, a lot of the Mars colonization enthusiasts, they argue that we have to send humans to space because we need a second planet to have humans on in case something happens to Earth. We need a planet B. Not a plan B, but a planet B. Now, this is nonsense as an idea. It just doesn't work. No matter what we do to Earth, we can never make Earth anything like as uninhabitable as Mars. We'd have to get rid of all the oceans, completely. No water left in any of the seas. And nearly all of the ice caps. We have to get rid of all the atmosphere, apart from a tiny, tiny fraction. We have to make sure there's no oxygen left in what's left of the atmosphere. We have to get rid of the Earth's magnetic field in order to allow masses of ionizing of radiation get through to the surface. And then we still wouldn't be quite Mars because we can't do anything about Earth's gravity, which is what we're used to. And the various other things we can't do. We're close to the sun, we get more sunlight. There's no way that this isn't just inconceivable that at any time in the next few centuries or 1,000 years that we make Earth as uninhabitable as Mars. And all these plans for terraforming Mars, I mean, why not instead use Earth sustainably? Work to, we have problems dealing with 0.04% of the Earth's atmosphere as carbon dioxide. And yet they're talking about transforming the entire Mars atmosphere into an Earth atmosphere. And even if you have an Earth atmosphere on Mars, then it has to be about 3 times the mass per square meter of Earth atmosphere in order to get the same pressure there. And it would have to be constantly supplied with artificial greenhouse gases, because with half the sunlight. Now you might think half the sunlight is hardly any difference, but it's a huge difference because it's the warming relative to absolute zero. And so half the sunlight means it's far, far colder on Mars. And even if you had an Earth atmosphere, Earth thickness atmosphere, there is no way that you would have trees on Mars. And it'd be very difficult to get you would get some liquid water, but you wouldn't get trees, and you wouldn't get anything like a modern climate. And you would need artificial greenhouse gases or huge mirrors. Mars is not just a fixer-up of a planet. It is. In fact, I have been very interested in the Moon for a long time, especially recently, since looking at this. And I looked at the comparison of the Moon with Mars to see which is best for humans. And I was expecting to say, oh, that Mars is the best, but the Moon is a good second best, and so we should start on the Moon and move to Mars eventually, once we've proven that Mars is safe for humans, if we ever do. But I found that it's the other way around. The Moon is by far the best, at least up to a few 100,000 people. Then the Moon is by far the best place if you want to try space colonization. It has, if you go to the hard vacuum on the Moon is an advantage. It means that you can deposit solar panels directly. You can actually make solar panels through direct deposition using techniques that are not economic on Earth, because it's a much harder vacuum than in any of our factories. It has double the sunlight of Mars. If you go to the lunar poles, then because the Moon by chance is almost exactly vertically aligned relative to the Sun, then the Moon hardly moves at all. So the areas, its axis hardly shifts at all. So it's tilted relative to Earth, but almost vertical relative to the Sun. A remarkable, rather nice coincidence, really. And this means that it has these craters of permanent darkness, where it gets as cold as liquid nitrogen. So ice on the surface of Mars, you'd lose, I think, 60 meters a day or something, a vast amount of ice every day, and just do it sublimating. There's no way that you can have ice on the sunny side of exposed sunlight on the Moon. But, so I said Mars, I meant the Moon. But if you go to the lunar poles, it gets as cold as liquid nitrogen. At liquid nitrogen temperatures, then ice can remain there for billions of years. So it's entirely possible that, and there is indirect evidence that there is ice on the Moon in the lunar poles. This needs to be confirmed, but this would make a huge difference to humans if there's ice on the surface there. But also extremely interesting for the search for life as well. People talk about going to Mars to search for life. We can go to the Moon to search for life, because these would be cold traps where life from early Earth, even for billions of years ago, the meteorites get thrown up into there, and there are papers that look into this possibility and confirm that it's a possibility. So the meteorites from early Earth can get thrown up and land in the craters of total darkness at the lunar poles, and then the organics will still be there. And I talked about how there's these bits of the Chicxulub asteroid, when that hit the shallow tropical oceans, it would have sent bits of ammonites and stuff like that to the lunar poles, and they should still be there. If you dig in lunar poles, you find little fragments of a few millimeter bits of ammonite and bits of other stuff from dinosaur era. They should be there. Even maybe bits of dinosaurs, who knows? And certainly lots of microbes. They should be there somewhere. Bits, a significant amount of the ice. If you dig and sift and look and sift and look, you'll find it eventually. And maybe even the DNA. Jurassic Park, it's not plausible at all on the Earth, because we haven't had conditions to preserve DNA for all that time. But it could be plausible on the Moon, at least for something like maybe ammonites, that we might be able to actually find the actual DNA. If you look at the people who have worked out the timescale for preservation of DNA on Mars, and applying those results, and in my Touch Mars book, I applied those results to the Moon, and this is my own finding. It's not published research, but it hasn't been peer reviewed. But I think that it would be possible to find intact DNA from the dinosaur eras and even earlier on the Moon. That's not very much damaged at liquid nitrogen temperatures, and it should be there. At any rate, the published research does say that there should be meteorites from Earth. There could be from Venus, if in early Venus had much less atmospheres, according to some ideas it did. Then impacts could have sent meteorites all the way to the lunar poles. And it could have early life from Mars. And of course, there's no planet protection issue there with this life from the Mars, from lunar poles. So that could be studied and then returned to Earth. At least I don't think there is. I mean, perhaps you need to look at it a little bit carefully, but it's hard to see that life could still be viable if it's been sent by a meteorite from Mars to lunar poles and it's been sitting there for billions of years. And so so we do have a possibility of astrobiology, interesting astrobiology, at the lunar poles. We also have ice that is a great resource for human beings, and then it's a great place to actually live because for human beings, because the temperatures, I think is it 20 below, something it's below zero, but the big problem for a human occupied habitat is to keep it cool, not to keep it warm. The ISS has great fins to try and to reject heat into space. So the lunar poles they're ideal. It's a perfect temperature for human habitat. And because it's sort of vertical like that, because it's just in complete darkness, you can have heat rejection panels that are horizontal. And in complete darkness, they reject heat vertically, don't have to move. You can have solar panels to capture the sunlight, and they could be mounted around a vertical pole. But it's a very simple thing. It would only return round once every 29 days, or whatever it is, the 28 days, the lunar day. It would just turn very, very slowly, and it would always be facing the sun. And you could put it up on a pole so as to clear any nearby obstacles, because you have these points near the sides of constant darkness. You have the peaks of almost constant daylight, and in those peaks, then if you could have a solar panel there, they would receive sunlight nearly all the year round. In the best places, they have a day or two in the lunar winter when it's in shadow. The shadow would be the shadow of maybe some nearby rocks, or maybe of a distant mountain. It just depends. There's some lump in the horizon that casts a shadow onto this spot. And so you'd have to have batteries for that time, or you raise your tower a bit higher, or you have two of them. You have one of them, you've got a distant mountain that blocks it. You go and put another one there, and then you beam the energy, or you have a cable leading from one to the other, and then you have the light all the time. You have power all the time. So there's no way on Mars anything like that. Indeed, Mars is a great problem with power. It has half the sunlight of Earth, and it also has the problem of these solar storms, which can last for weeks on end, and even longer, and they block out 99% of the sunlight, of the direct sunlight, and a high percentage of indirect sunlight too. And this means that even if you do have solar power on Mars, you can't rely on it for a human colony, but you can rely on it for a lunar pole colony. And the numerous other examples, advantages I go through in my case for Moon first. I do a comparison with Mars. You can do commercial exports from the Moon to Earth. It's quite low cost, and especially if we do the Hoyt tether system, which is two tethers, one in orbit around the Earth, which can like a bowler, it can shoot, it can throw, it can lift a supersonic, a hypersonic plane from the Earth's atmosphere into orbit, and as it spins around, and then the other end it captures things coming back from the Moon, and then at the Moon end you have a bowler which can be synchronized so as to drop material to the lunar surface. It's actually stationary against the lunar surface that throws things back to Earth. And the interesting thing about this is it is powered by the motion of material, because the Moon is high up in the Earth's gravitational well, and it is sending, as long as you send more materials from the Moon back to Earth than you send from Earth up to the Moon, then you actually you can generate power from transporting materials from the Moon to the Earth. Instead of using power, you actually generate power by sending materials, which is enough to keep the system going. And it constantly gets boosted by the incoming material. Hoyt has worked this out in great detail, how this can actually work. And it's much easier to build than the space elevator. It uses materials we already have. It's not very heavy. It's much lighter than that. I think if you did missions, if you had exports every day for a year, every week for a year, I think that is already enough to make it worthwhile on a mass basis to build the Hoyt tether system to send exports from the Moon back to Earth. So the Moon has possibly very cheap exports back eventually, whereas Mars has nothing like that. Well, there is a possibility of something like the like the there's a possibility of a cable being descending from Phoebus or Deimos almost to the lunar to the Mars surface, and then going up again, and then from Phoebus and Deimos, the two of them kind of piggybacking, cycling together and sending material all the way back to Earth. But that's a far more difficult thing to build, and in the near future at least, it'll be so expensive to send material back from Mars. And the Martian and the Elon Musk, for instance, he's not suggesting that Mars could pay for itself by exports. He's suggesting it could pay for itself by exporting ideas. I do not see how a colony can pay for itself by exporting ideas, no matter how brilliant the people are there. They're the highest far higher technologies than we are. They need ideas far more than we do in order to develop their technology and use it. They'll be patenting, they'll be licensing Earth technology. But if it is, then the moon people, they'll have as many brilliant ideas as the Martian ones, with their challenging, and so they can have if it is possible to pay for yourself by ideas, you can do that on the moon too, as well as all the exports from the moon, the numerous ones. There's ice, there's a possibility of platinum, there's many other things. I go into it in my book, I won't talk about it now. So anyway, that's why I'm saying we should go to the moon, and then and going to Mars is extremely dangerous. To send a human mission to that, it's not just the well-known danger of humans landing there, it's the danger of the transition from here to there. It's like spending 2 years in a submarine, but you are not permitted to go to the surface. You can't vent the air. You're surrounded by complete vacuum. If there's a fire, if there's a chemical release, you've got to deal with it in your submarine. You can't go to the surface. You can't get help. There's no way of getting back to land. You're committed all the way to Mars. As soon as a Mars mission leaves Earth orbit, it's committed, and it can't return because that would be too much fuel. So it's like the Apollo 13 scenario, but your only way back is around Mars instead of around the moon. And I don't think we're ready to do this. I don't think we should do this. We get many life support problems with the ISS already, and they get solved, yes, but they get solved because we've got easy supply from Earth. And I think we need to have as one astronaut said, that we could send humans to, or the Canadian astronaut, I'm sorry, my names skip my mind even when I know them very well, but you must know the famous Canadian astronaut who does all the photographs of Earth, and who anyway, and is one of the commanders on the ISS. Name will come to me in a minute, but anyway, he said that if we go to, if I look for canoe, if I search my page for canoe, and I think I've got a quote from him here, it's rather fun. Oh, I've got too much loose for canoe. Oh yes, that's it, I found the quote. It's a rather nice quote. I'll just go back a bit, I'll soon find it again. So here we go. Chris Hadfield, that's it. Yes, so he said, I think ultimately we'll be living on the moon for a generation before we get to Mars. If the world and the moon were threatened, and the only way to preserve our species was to launch from Earth, we could go to Mars with yesterday's technology, but we would probably kill just about everybody on the way. It's as if you and I were in Paris, paddling around in the Seine in little canoes, saying, we've got boats, we've got paddles, let's go to Australia. Australia? We can barely cross the English Channel. We are sort of in that boat in space exploration right now. A journey to Mars is conceivable, but it's still a lot further away than most people think. And I do not think that Elon Musk's starshot changes that. It's still way, way beyond. He first needs to show that he can send human beings safely to the moon, which is a huge challenge. And then once he's got people sending people to the moon, he's got to show that he can actually keep them safely there, just sitting in his spaceship for 2 years, without any supply from Earth. They just go to the moon, they've got their supplies with them, they've got some food in there, they've got their regenerating system for the atmosphere, and they just sit on the moon without any supply from Earth for 2 years. If he can do that, then his spaceship is beginning to be ready to go to Mars. You still would probably want to send 3 of them in case something goes wrong with one of them, and go in a little armada of 3 spaceships going to the moon, going to Mars in one go. And so that's the sort of order of, and I think this is not likely to happen in the next generation. If you talk about generation of astronauts, like sort of 20s or to 40s young astronauts, I know you get older ones as well. But I think, or if you're generation of children, so I think if you understand this generation in that form, so by the time that, if we were to start sending human beings to the moon today, then I think by the time our youngest children are 20, then you may be able to start sending humans to Mars orbit. I think it's of that order to be reasonably safe. So I don't see humans going to Mars orbit before maybe about 2040 myself, unless we get very remarkable advances in technology. But it could be 2030 if it goes very, very fast. But that's assuming very, very fast, like if we had a very, very fast program to send humans to the moon, we need to do that first. If we had humans to the moon in the early 2020s, maybe we get send humans to Mars orbit in the early 2030s, but I would think more like in 2040. And then, if we can send humans to Mars orbit is the place to go first. Because if we send humans to Mars orbit, then they can search the surface via telepresence, and especially by technology we have by then, 2030 or 2040, then we can surely send thousands and thousands of tiny little spacecraft to the Mars surface. And I think we can achieve 100% sterile landers. Now the reason is because we know how to make a lander for Venus. We already have plans. We can nearly make a complete rover for Venus. Indeed, there are ideas for a way to do it, and there are ways of doing it. One that is cooled. We already know how to make all the components for a cooled rover for Venus, which would be at 300 degrees centigrade on the surface. At 300 degrees centigrade, then such a rover would be sterilized very quickly. That's far higher than the Viking rovers were baked at. And if you could send it travelling from Earth to Mars at 300 degrees centigrade throughout the journey to there, all the amino acids would be disintegrated at 300 degrees centigrade. You're not just talking about sterilizing life, you're talking about disintegrating the amino acids. And just keep it at 300 degrees centigrade for 6 months, and there's no way there's going to be any life there. So this is actually using components that we have today. It's not talking about developing any new components even. It's just about designing a spec for your spacecraft. Say this spacecraft has to be capable of 300 degrees centigrade operation conditions, like a Venus lander. And then heating it to 300 degrees centigrade, and we can have 100% sterile Venus landers from Mars. Now, I know some instruments will be very hard to make compatible with these requirements. Maybe they need to be sterilized in other ways and in some ways joined to it. And of course that then gets very difficult. And think about how you manage to make them together so they can actually work on Mars. And especially if you have some kind of chemicals like the labeled release, and those chemicals could be destroyed by the high temperatures, so you would have to add those later in some way that made sure you didn't recontaminate it. So there are obviously quite a lot of things to be thought about if we do to have 100% sterile landers. But I think if we start on a program to do this, then within a few years we will have 100% sterile landers, and very small ones that we can send by the thousand. And if we want to do a thorough study of Mars, we don't want to have a 1% chance or even a 0.1% chance for each, or even a 0.01% chance for each mission that it contaminates Mars, because over thousands and thousands of those, then there's a high chance that one of them does contaminate Mars. So I think we should, if we want to have, the problem is there's so many different habitats on Mars, vast numbers. There's, I described a couple of them. There's the RSLs. There's the possibility, for instance, at the lunar poles, this doesn't get nearly enough attention, I think. But in the polar regions on Earth, then you get liquid layers of liquid water are forming just below the ice. That is due to the solid state greenhouse effect. That light goes through transparent ice. So if you have transparent ice on Mars, it would be the same there. Blue ice on Earth. It is semi-transparent. Light goes through it. It heats it up. The heat radiation is trapped, and it starts to melt. And it melts, I think, up to half a meter below the surface. On Mars, it would be a little bit closer to the surface. And they've done modelling of this situation on Mars. If we have transparent ice on Mars, then we have liquid fresh water on Mars, trapped by that ice. The models are pretty clear. What we don't know is if there's transparent light on Mars. But there are possibilities that there are some indications. Some think that the Martian geysers, that the fast-flowing dark streaks that you get, that after you get the Martian carbon dioxide geysers, which are carbon dioxide being thrown up into the atmosphere in Mars, which was dry ice that then evaporates and produces these geyser effects. And then in the debris from the geysers, where there's lots of salts, then you get these streaks that move up to 5 meters a day, and they're very fast-moving streaks. And these streaks may possibly be the result of ice that has salts beneath it and the ice on the top, and then this greenhouse effect causing it to melt. The various other ideas, but it's thought to be. I think the two ideas, and that's one of the chief ones. It is in some way that it's trapped brines that are streaking out onto the surface. In Richardson crater near the South Pole, it's a different mechanism for the ones near the North Pole. So, and the numerous other, I've got a list of about a dozen or so in my book, but I don't think it's not at all exhaustive. And now imagine trying to search those, then, and you want to send several to each one, then the different, like the RSLs, there's some in that great trench in the equatorial regions, and there are others in the polar regions. And you need to send several different ones to get a reasonable first approximation. And I think we will not know if there is any life on Mars until, for sure, until we have done a reasonable survey, at least sent probes to all the main different possible places where life could be. And that includes caves. And there's a wide variety of caves that are possible on Mars. All the possibilities on Earth, including ones carved by liquid water, because there have been times in the past when liquid water has flowed on Mars. And also ones that are by direct sublimation of ice into the atmosphere, and ones that are direct sublimation of carbon dioxide into the atmosphere. And we have caves due to fracture faults, like the shifts and lava tube caves, and ones due to the sulfuric acid carving out rocks, and all of these are potential habitats on Mars as well. And to do a really thorough job, you want to look at least a few of each of those kinds of caves as well. And I mean, if you find a very habitable habitat early on and there's no life in it, you begin to suspect that probably life hasn't evolved there. And then as time goes on, you get more and more convinced. But you might find life early on, very early on, right away too. And then if you do find life, then you want to have a pretty thorough biological survey of Mars to know what the effect that Earth life would have on it, or it would have on us. Now, all that could be done very quickly if you had humans in orbit, because they can do tele-operating of avatars on the surface. It's almost like they're there. In fact, in some ways, it's better than being on the surface there, because they don't have to put on a spacesuit. And it takes ages and ages and ages to put on a spacesuit. It's not easy. And they have to be maintained. And the Mars dust will get everywhere, and they're very, very expensive and difficult things to maintain. It's far easier to send an avatar robot going around on the Mars, and the advantage of the humans being there is that because you're in orbit, you have very little time delay between the thing on the surface and what you're controlling, either from Phobos or Deimos, or you would do it from an independent orbit. A sun-synchronous orbit is very nice, and that's the Herald mission, where it goes in orbit that every day, twice a day, it comes down over the sunny side of Mars, which is the opposite hemisphere of Mars each time, because Mars, of course, every Martian day, so Mars is rotating, and half a day later it comes on the sunny side and the other side. And it's a slanted orbit, because it's sun-synchronous. It's designed to be always synchronous with the sun. And so it always comes in on the sunny side, and that needs to be a tilted orbit, so it goes past the lunar poles every day, both poles. So at a somewhat greater distance. This is a wonderful, very exciting, very interesting mission for astronauts, where Mars would be very small in the distance, then it comes, and then you come in, and then you zoom in very close, right close over as close as you want, as you like, to over, by actually skimming into the atmosphere, over the equatorial regions on the sunny side, and then you go out again over the poles. And it'd be a very exciting and very interesting mission. I mean, if it weren't that I'm a bit claustrophobic, and I don't think I would pass the claustrophobia test, and I'm big too old and all that sort of stuff, I'd love to be on such a mission as that. I knew if I could pass the astronaut exams. I don't mind being in small places as long as there's a window, but I don't think I would be able to pass the exams on claustrophobia for astronauts, because they would have to be able to tolerate small spaces without windows. I couldn't do that, sadly. So I'll probably never be a NASA astronaut, though I could be a space tourist someday, you never know. But anyway, that would be a fantastic mission and wonderfully exciting. You know, think about how interesting it is from Earth, and this be a completely new planet. So I see it as something like that. Humans to the moon in the 2020s. Humans to Mars orbit, maybe the 2030s, and if by late 2030s maybe, and if by then we have already discovered life on Mars, then we would already have missions by then where people are doing life detection missions on the Mars surface. I don't think we should send a sample, return a sample from Mars. I don't see the point. I think we should do life detection first, at least from the astrobiological point of view. If we find life there, then having done that, then we know what to return. Then we can return it, but not before then. There's no point. And if we do return it, then at least, I mean, some point for the geologists, but it's so extremely expensive, far more expensive than the world's most expensive diamonds, millions of dollars per gram sort of thing. So I think we should. I don't think we should return the sample from Mars. I think if it was my say so, I would just yank out this sample return container from the rover, the 2020 rover, and replace it by something else, life detection suite of some sort. Of course, it's not my say, but I don't think they are going to return it, because it's going to cost so much, and because they're going to discover it's not legally possible to do it. So I don't think it's going to be returned, in my own view on the matter. And we'll have other instruments that find stuff about Mars far better before they could ever return it. But at some point we will return samples from Mars, and I think we should return them if we know what's in it and we know that it's safe. Then we can return them to the Earth's surface. If not, or if we think it's unsafe, if we discover life there that can live in human lungs or something, then I think we should return it to above geostationary orbit. That is the safest place in the entire Earth-Moon system, as far as I can tell. Well above it, not just 200 miles above it, but maybe 100,000 kilometers away from Earth, something like that, maybe a third of the way to the Moon. Because that would be as far as possible from either the Moon or the Earth. It's very difficult to get from there to it's yet very easy of access from the Earth. But because just as easy, almost as easy as geostationary satellites, and we could then have a big spaceship there where you get the samples returned inside. It just start off as a small one, and then it can expand, or it could just be one of the Elon Musk Starship spaceships. Just goes there and sits there, and then you send instruments to it inside it, and you just buy one. He says it's not going to cost very much to buy one of his spaceships, so much less than the cost of Curiosity, say. So you could just buy one of these spaceships and put it there if he's correct in his projections, and then you just return sample to that spaceship. You've got loads and loads of space, and then you send instruments from Earth up there, and with the spaceships you can send huge amounts of material up there to examine it, huge instruments, and then you would operate them tele remotely from Earth. And that would be a completely 100% safe way of studying even the most hazardous forms of life. I think that's how we should do it. And so anyway, that's how I think we should do it. And in any case, you do not need to worry about NASA returning a sample from Mars. They're not going to be permitted to do it. There's no way they're going to be able to permit to do it unless we find a way to do it safely, which could be either by detecting life on Mars, and then if we do detect it there, we find out what it is, and then if we know what it is, then we can design all our protocols based about it. What makes it so extremely difficult and so extremely complicated, and the legal protocols so difficult and everything, is that we have to design a way of returning a sample where we have protection against any conceivable alien biochemistry. That's what these people are being tasked with. When you ask an astrobiologist to design a sample return building for that can take any materials, take a sample, even 1 gram returned from Mars, they have to design a facility that can contain any conceivable alien biochemistry. And that's a tall order when we only have one biochemistry that we know of, the Earth biochemistry, which is very specific. But if we have a known biochemistry, which we have studied on Mars, then that's a totally different order of problem. Then you know what you have to return. And I mean, for instance, if what we find there is early life that hasn't yet developed into separate species yet, for instance, then we might well be able to decide early on there's absolutely no possibility of any risk to Earth life from returning it, and we would just then be able to return it straight to the Earth's surface without any problems at all, and our entire Mars receiving facility building, which would cost $1 billion to build, would be unnecessary. So that is a totally possible thing. In fact, I think that's quite a high probability, maybe a 50% chance that what we find on Mars is like that. But it's not a high enough chance to say that it's safe to send astronauts there, because there's the other 50% chance. I mean, maybe you can say it's 33%. 33% early life, 33% no life, 33% present is life. Just saying, because there's no way to work out probabilities, so just say they're all equally likely. I think that's about as best guess as you can get. But there's another possibility, as well as the early life. There's a possibility of uninhabitable habitats, and that's an idea from Charles Cockle, and I think that's a fascinating idea. And that is the idea that you could have biochemistry there, you could have chemistry there, but there isn't any biochemistry there yet, because there isn't any life there. So and then people sometimes seem to think that if there's no chemistry there, if there's no biochemistry there, it doesn't matter contaminating it. But I mean, that is extremely interesting. If you have an Earth-like planet, a planet like Mars, which is as similar to Earth life as Earth is, and if it's had chemistry there that's developed for billions of years, and there'd be evidence of earlier chemistry as well, and there are all sorts of ideas about what chemistry would be like before you get life. So there's certain kind of very large crystals, Oswald crystals, for instance, those might be there. There's certain kind of things that look like cells but aren't really. There's autopoietic cells which are almost life but not quite. There could be all sorts of vast numbers of things that we can't create, because they have to be, it's not just evolution that takes a long time. You can have chemistry that evolves for a long time as well. Chemistry that just works away for hundreds of millions of years, and something comes out of it that you just couldn't get in like a few minutes of mixing things in a litre or two in a lab. So I don't think we can predict what the chemistry will be like on Mars in detail if we haven't until we study it. Again, maybe it's totally uninteresting. Maybe it is uninhabited habitat. Maybe it is an uninhabited habitat with a totally uninteresting chemistry. Now, in that last case, then it's still, you need to be careful sending life there. The reason is because Earth life is going to transform the planet. So people talk about, for instance, making Mars more habitable for Earth. What happens if you introduce some life there that produces sulfur dioxide in large quantities? Then sulfur dioxide is quite poisonous. Don't mean sulfur dioxide, I mean hydrogen sulfide. It produces hydrogen sulfide in large quantities. And that's not very pleasant gas to have in the atmosphere if you're going to want to have humans there. On the other hand, it's quite an efficient greenhouse gas, so you might do that deliberately in order to warm up the atmosphere a bit. But I mean, this is something you want to plan. You don't want to just send humans there and just whatever microbes they bring with them, just randomly, willy-nilly. That is the life that starts off on Mars. So this is something that needs thought and consideration, even if there's no life there, but there are habitats for life there and they're uninhabited. I think you still need to think about this. Maybe it's no problem. Maybe it's absolutely fine sending just a bunch of whatever Earth life you happen to have with you. But it might be that it has significant future effects. It could also work the other way. For instance, if you send your blue-green algae by mistake, then they can start producing oxygen using carbon dioxide when you're wanting to have carbon dioxide. But the other way, you can have predators. So, for instance, you want to create, you want to cover Mars with green algae to produce lots of oxygen at some point. But then what if you've got stuff that eats that algae? And so there are all sorts of interactions that can happen. Then, as well as that, you send humans to Mars, they land on the Mars surface, then most of the microbes that end up on the surface are going to be in some way microbes that are adjusted to the human habitats, all the human bodies and our crops and so on, just because that's what you've taken there. And even worse, you might well have a crash on Mars, and we have to make Mars safe, even if human beings crash on Mars. And that means, like the Challenger accident, human bodies spread out over the surface very sadly, and all the spores and all the bits and pieces of so on and so on. But it's either that, or it happens more slowly and leaking out from a habitat. Now, if you do it like that, then you're seeding Mars with microbes that are very accustomed to living in human habitats, and even ones that are used to living in human bodies. And they're not necessarily ones that can't survive on the Mars surface. For instance, one of the best candidates for a microbe to be able to withstand the very low pressures on Mars is actually, I think, was originally isolated from the human tongue. But it just happens, for some extraordinary reason, it's just coincidence, that it's able to withstand very low pressures, conditions that it has never experienced on Earth. And by the way, the Mars life could easily be able to withstand very high temperatures. There's probably hydrothermal vents, there certainly have been in the past, and maybe even today. There's very possible, and then the life that's come from that could get onto the surface and retain its capabilities. There's people who say that any life from Mars is going to find Earth too hot. There's no reason to believe that. Absolutely none. And that's just like saying that any life in Antarctica must be incapable of surviving in the tropics. That's not true. I shared that picture of a lichen that survives very high in the Antarctic mountains and also found in the Mediterranean. And that can be absolutely the same on Mars, as well as the conditions in daytime do actually come up to 20 degrees centigrade in places on the Mars surface in the daytime. So if you had lichens on the surface, they might actually experience quite high temperatures. So it's entirely possible that Mars life comes back to Earth. And so anyway, I talk about some of these things in my paper that I was told you about, and some things in my book, and I've also got my article, and I didn't actually say what the timeline was, but if NASA were to start the legal process of returning a Mars sample to Earth, then I worked out, just using my best guesses of the timescale of the different, I looked up how long it typically takes for these laws to pass, and I looked at the list of laws that had to be passed in the sequence and order that in that paper that I was telling you about the entire legal process needed to return a sample from Mars. And then I added on the timescale of the studies we have for Mars return already, and each one, the NASA one, the US one, and the ESA one, the European one, European Space Foundation one, each time they've got more and more stringent as we find out more. The reason is because we keep on finding out more about the capabilities of Earth life. For instance, the latest one, the ESF one, we had discovered the previous one they discovered the ultra microbacteria, I think, And with the ESF one, they discovered how very rapidly genes can be transferred between microbes in seawater. So they then said that we have to contain not just the microbes, but even the gene transfer agents that can use to transfer genes horizontally between Mars life and Earth life if they happen to be related. And this made it hugely more difficult, more complicated to design the containment facility. Each one, we find out more about Earth life, we find out more about possibilities for biochemistry, and the more we find out, the more difficult it becomes to contain. And so it's entirely possible that it's not likely it's going to be less requirements, it's likely to be more requirements, if anything. And based on the latest study of that nature, then I figured out that if we start in 2020, and then you look at the requirement that you have to build a facility, which NASA will only do after we know what we have to build, and then you have to have it running and make sure that people are familiar with it and they're not going to make all these mistakes in quarantines and while they're running it. And then only after that you can launch a mission to Mars. You have to do the launch after everything is known to work. You can't launch them while it's being built. You've got to do the launch after it's all done, according to the latest study, and then that has another 2 years as well on top of all that. If you add all those two together, then it takes us to 2040 from now, before the sample can be returned to Earth. And since they want to return it before 2030, I don't think they're going to return it. Either that, or they return it sterilised. And it would be possible to sterilise it in the return journey, but if they do sterilise it, then some of them think that this will remove some of the interest, but it is not designed as a biological sample return anyway. They have not sterilised, they're not going to sterilise the sample return containers the samples are put in. There's a small possibility of a viable spore in one of the sample containers. They haven't yet sterilised it. And so and if you get a microbe in it, then people sometimes say that if you have a microbe returned from Mars, that you can tell if it's from Mars from Earth by looking at its gene sequence. You can't. That's not possible. The reason is because only a tiny fraction of a percent, I think it's 0.001%, I can't remember how many zeros, percent of all Earth microbes have had their gene sequence. And there are many entire genuses of entire groups of microbes that are only known by a few fragmentary fragments of RNA that have never been cultivated, and they don't even know what they look like. They just find little fragments of RNA which suggest that these extra groups exist. And then there likely to be other ones that we haven't even discovered yet. So if we got life that came back from Mars, and we looked at it and it's not related to Earth life, it's likely to be decades or even longer before we know whether or not it is contamination from Earth or whether it actually genuinely comes from Mars. If it is related, of course it's unrelated, we know, but if it's related, we don't. And in case you think that, but the Mars spacecraft don't have unusual life, they actually do. If you look at the spacecraft assembly facilities, which they do an awful lot of sterilising them, and in the process of sterilising, they actually encourage these extremophiles, not intentionally, but it's a side effect. And they are extremely diverse, and it's also depending on the local conditions. For instance, the JPL facilities, then they have desert species that have come in from the nearby desert, but they rather more than in other facilities. But they have a very wide variety, and there's no way they can do a complete census. They can't do it. They can't do a complete census of all the microbes that could be on a sterilised spacecraft sent to Mars. So if we do find life returned in the sample return, we won't know if it's from Mars or from Earth, if it's related, because it's not sterilised. It's not sufficiently sterilised to have that confidence. So I'm not sure they actually lose very much by sterilising it, because it's not really designed as an astrobiological sample return. It's really designed as a geological sample return with the astrobiology as a kind of add-on, without really that much consultation. I don't think there can have been much consultation with astrobiologists, because it's just not designed in the right way. And so maybe they return it sterilized, and they could return it. They could use my idea of returning it to above geostationary orbit, an idea like that, and they sterilize half of it and send it back to the Earth's surface, leave the other half there, and then return that half back to Earth. But because of the way it's been designed and done, because it's very unlikely that it finds any life, because the rover has not got life detection instruments, and it could drill a sample from a rock only 1 centimetre away from a patch of life, and it wouldn't find it. So I'm not sure even if it's worth leaving half of it unsterilised. They could just sterilise the whole thing, which is a much simpler sample return. So that's a possibility. But anything else, then... by the way, if you return a sample to above geostationary orbit, you would not need to pass any new laws. That can be done under the Outer Space Treaty. Because it's only if you return life from there to Earth that you have to look that the Earth environmental laws come in, and the Outer Space Treaty is only about returning harmful contamination to Earth. Returning harmful contamination to a spacecraft well above geostationary orbit, as long as you do it carefully, and there are ways of returning it carefully. You obviously wouldn't return it by aerobraking, that would be very stupid, because the aerobraking, if it went slightly wrong, it would hit into the Earth's surface. But there are ways of returning it safely, returning it to an Earth retrograde orbit is one of the good ones, like lunar orbit but retrograde. And that's quite an easy orbit to return to from Mars. And then you return to that, and then you can go from there to it's not retrograde about the Earth, but it's retrograde about a lunar retrograde orbit. It gets into an orbit retrograde about the Moon, but prograde around the Earth. And that is the one you can very easily transform into a geostationary orbit. It's an easy orbit to get back into, and although it looks like it's orbiting the Moon, it's actually orbiting the Earth in the same time period as the Moon, but sometimes going outside the Moon, sometimes inside it. And that's a nice orbit to return to. And then you could then go from that, transfer from that. You could also return to the L1 or the L2 positions around the Moon, and those also be quite nice ones to use. Then you could actually study them, but they're not stable long term. So, but the nice thing about above geostationary orbit is it is stable long term. That's why even millions of thousands of years into the future, I'm not sure about millions, but you'd be it's a very, very safe orbit to return it to. And so that's that is something we could do even with the Mars sample return, with the NASA sample return. I'm just not sure if it's worth it, but it would be possible to do that. And so I think maybe that's what they will do. And certainly if it's interesting, if we discover interesting life on Mars, and we've got this sample sitting on the Mars surface, and then we could return them to above geostationary orbit. Now, and that can be done within the Outer Space Treaty, and without even defining Mars. You wouldn't need to define Mars as Category 2 for that. You can keep Mars as Category 5, Category 4, and the restricted Category 5 for sample return, meaning that you have to take all these precautions to protect Earth. You could do that consistently with returning to above geostationary orbit. And if NASA is really set on returning their sample, or we find that they're really, really interesting and we need it, then that's what I think we should do. And then sterilize it if necessary. Is there anything else that I want to talk about? I think that's about it. If you've got any questions, then do say in the comments. I'm going to upload this to YouTube. I know it's quite long, and but hopefully it was quite interesting as well. And I do hope that we get... obviously, I don't have any say on NASA and what they do, but I do hope, I want to raise awareness in the general public of these issues, and people just start thinking and talking about it, and we will make the best decision if we have all the points of view on matter being heard. And so I'm not saying that they've got to do what I'm saying. I'm just bringing aware various thoughts and ideas that some of you may not have I've actually brought to mind and thought about. You can go and have a read of my book. It's 1,000 words. It's 1,000 pages, so it's quite long. But it's quite easy to. It's organised to be easy to find sections in it, so that you can jump to whatever's interesting. I've written it to be as self-contained as possible. I'm not sure if you're interested in reading my paper personally. Let me know, and I can share it via. I can share the Google document with me. I'm wondering whether or not to share it to a preprint, like with archive. I'm not associated, sadly, with any academic institution. It'd be difficult for me and just now I've just got a huge amount on of other considerations. I don't have the time to finish it, but I hope someday to submit it to an astrobiological journal, and hopefully it'll get published at some day. But I just don't know when I'm going to be able. And I've been encouraged by an astrobiologist friend to do this, and so that's my plan for the future at some point. But I don't know the time scale for that. Anyway, that's it. Thanks for listening. I hope you enjoyed it, and at least I am confident that there's no risk for Earth. I have some concerns about there being some risk for studying Martian astrobiology if they go ahead with this category 2 categorization, because I think it's potentially very vulnerable to Earth microbes. And I think we should. I think that actually, as a high priority, we should study the effect of our current sterilization on Mars. I think a good mission to do would be a well-sterilized mission to the Phoenix lander, to study the Phoenix lander and see if there is any. See the Phoenix lander landed in a region that at the time they thought was completely safe for planetary protection, but then Phoenix lander was the one we began this whole chain of discoveries when it found that there was ice just below the surface, which was unexpected, evaporating in the thin atmosphere. It discovered very clear pictures of the perchlorates and what the salts are composed of, which led to these detailed modelling of brines there. It had salts thrown up onto its legs, and those salts produced little. They deliquesced. They took up salt from the atmosphere. At least that seems to be what it is. And they became liquid droplets. It could otherwise be salt on top of ice, but either way, it produced these little droplets of what seemed to be liquid, but sadly Phoenix could not analyse these liquids, and so it's not possible to say definitively, but people are I think it's pretty much certain it is actually liquid brines that they found on its legs. And then it did this remarkable isotope measurements of the carbon dioxide in the atmosphere, and you would be surprised how much you learn from studying just one molecule and the isotope ratios. They found that it has come from volcanoes recently on Mars, so there's active carbon dioxide coming, and then they found that the oxygen from it has been exchanged with something on the surface, which has to mean some interaction with water. So, or at least that's the most likely. It's hard to think of other things that would do it. So it was very clear evidence already in 2008 that there's liquid water on Mars. They weren't able to say whether it's present year-round every year, or whether it's present every year, or whether it's only present a few times every 1,000 years or a million years or whatever. But the later research is now showing very clearly that there are liquid brines there present every year. So that's why Phoenix then was discovered. They discovered that Phoenix is not in a safe place for planetary protection, and it was not adequately protected. It should have been totally, thoroughly sterilized like the Viking landers. Instead, it was just partially sterilized like the Curiosity, relying on the harsh environment of Mars to do the rest of the sterilization. But where it landed, there are possible habitats exactly where it is. So, and then it was landed in such a place as the advancing carbon dioxide dry ice in winter crushed it, and all its panels were crushed. Its solar panels were crushed, and these are conditions that are kind of almost optimal for kind of getting bits of the Phoenix lander into nearby habitats, if there are any. So now it is still not very likely that it has contaminated Mars. The reason being because the conditions are very harsh. It was reasonably sterilised. There will only be a few spores left, and you would want some of those to be able to reproduce in the very unexpected Martian conditions. So it doesn't mean it's contaminated Mars, but it would be an excellent place to go to study Mars to see if there has been any contamination. If there has, it might need to be need to be contained. It probably hasn't spread very far, even with all the years since then, because of the very harsh conditions there. And so I think that this would be an excellent mission to do, because I remember I said earlier on that one of the problems with motivating sending life detection missions to Mars is that you could easily have a zero result, and it's very difficult to explain to the general public why you spent hundreds of millions of dollars on instruments to send them to Mars to detect nothing, even though that is extremely significant. Well, if we do it as a dual, testing planetary protection as well as searching for life, then I would suggest land well away from the Phoenix lander, but at the same site, which is biologically interesting, and actually drill below the surface as well. So we need a drill to 2 meters, and this is like the AFAIK Mars mission, which Chris McKay suggests, and which has sadly never been proved, but it's a very interesting mission to drill and look for past life that may have been cryopreserved below the surface. So we send a mission to do that, but it's also a rover like the ExoMars, and then this mission also would land well away from Phoenix so as not to be skewed by any contamination from Phoenix, like a few miles away. And it would drill into the ice and it would do all this interesting stuff about finding what's below the surface. And then it would trundle over to the Phoenix, and it would use all its instruments that it's got, life detection instruments, not just biochemistry or not just chemistry instruments, and it would look at the Phoenix lander and examine the lander itself, and examine the habitats near it, and see if it can find evidence of life there that it didn't find before. And if it does, and especially if it resembles Earth life, and it is different and it didn't find it before in the previous location, that would be suggesting that the Phoenix lander has contaminated Mars. And on the other hand, if it doesn't find it, then that suggests that our sterilisation is working pretty well. And it could actually go up then and look closely at actually bits of the Phoenix lander, pick up some of the chunks that have got broken off, and look at them and examine those and see if there's any life on those as well. And that would give an idea, and then in that case you would expect to find something, because it's not completely sterilised, but that would give an idea of how viable life is on a lander after so many years, how long it survives. And that's very interesting in the Martian conditions as well. So you would get very interesting science on planetary protection, even if you get a total null result for the discovery for Martian life. And so I think this should be a high priority mission. I think we need a high priority mission to search to test back planetary protection. And I think searching for life in situ on Mars is high priority. I think this would be a way to combine the two. It's not the optimal place to search for life on Mars. There are other places where it might be, we just don't know. If these salt ice droplets are there, and Nilton Renner with his experiments thinks they may be almost everywhere on Mars. If they are, then, and if they occur naturally, not just as a result of the stuff being thrown off from the ground, which seems reasonable enough. I mean, it's probably not just Phoenix landing that makes these droplets, if there are little droplets everywhere. And as he said, a little droplet is like a vast swimming pool for a microbe. So we might find Martian microbes there. And so it is quite good, quite an interesting one. And I think this would be a good next mission. I think we should do multiple future missions searching for life in situ on Mars. And this might be a good follow-up from Mars lander, or for anyone else who is coming in on this, who wants to start studying it. Like, for instance, Russia and China, they're both interested, and India. Maybe India, after it's sent a lander to the moon, can send a lander to Mars, and maybe even private space. And I think private space should be interested in this and want to learn out about it, not just for the biochemistry, for the if there's biochemistry, it could be of commercial value. It could be some commercial value of whatever life is there, whatever it is. It's something new we don't know about. And also for the safety of the astronauts. You can discover that whether Mars is safe or not by just landing astronauts there and see if they die coughing of something that is destroying their lungs. Or you can do it by sending a mission to the ground surface which looks there and looks and sees if there's anything there that could be harmful to Mars astronauts. I think the only ethical way myself is to send the instruments and not the humans. I don't, even if you've got volunteers. And then if you send humans to Mars, remember, they can't come back until they prove that it's safe. There's no, you could, with the current very weak outer space treaty, then it would probably be quite hard to actually stop a commercial space from sending astronauts to Mars, if they really, really wanted to. Because the treaty, as it is stated, just says that the government has to tell them to stop. It doesn't actually give them the powers to stop them. Or no, it just says the government has to warn other countries. So if an astronaut is setting off from Mars, then the US government is required to tell the other nations that this astronaut is setting off to Mars and this is going to impact on their experiments. And legal lawyers who look at this very carefully, then it doesn't actually specify that the government has to stop them from doing that. Now, the legal case goes back and forth, and some people say that it actually does specify that, but it just hasn't done that explicitly. And others say that it doesn't. And it's a matter of comparing two clauses in the treaty. I think the majority view is that it does require them to stop the astronaut from doing that. But there's a minority view that it doesn't. And it would be quite a big legal case if it ever comes to law as to which it actually is. So that's Laura Montgomery, I think it's the name of the lawyer, who argues that the only requirement in the Outer Space Treaty is for the United States to notify, say, Elon Musk, notify the other nations that Elon Musk is planning to send an astronaut to Mars, and it isn't actually required to stop him. But most astronauts, most lawyers would say it is. But either way, whether it's permitted or not, they wouldn't be permitted to come back again. Not if there's the potential of bringing Mars life with them, not without going through all our very strict and bulletproof environmental protection laws for Earth, which are not going to be bypassed. And the Mars colonization advocates might go along gung-ho to these public hearings and say we have to send astronauts to Mars because we need to have a second planet. But that's not going to work. That's just not. You're not going to get lawyers saying, "Oh yes, you're right. We've got to have a second planet for human beings. So therefore, forget all these laws." It just doesn't work like that. Law doesn't work like that. And as I said, it's not a valid argument anyway. So there's just no way that this is going to happen until we know what's on Mars. So we have to send. We have to study Mars in situ with life detection instruments there. I don't see any other way around it. It would just take too long returning samples because you don't know where to look, and you could be spending 20 years sending missions one after another, returning samples from here, there and everywhere. Whereas in situ you can just go and drill and move and drill and move, and just look around wherever you like and study in situ, and you could get all that done and very, very quickly if you've got an astronaut in orbit. So even if someone recklessly wanted to send astronauts to... So I think the private space should be behind this. And there's so many places where you can send private space. I said there's the moon. And after the moon, I don't think Mars is the most habitable place for humans. Even if I'm wrong about the comparison, then Callisto is far, far better if we can send humans there, because it's protected from the ionizing radiation. It's inside Jupiter's sphere. It's got loads and loads of ice and lots of organics. You can drill below the surface. You can melt an underwater lake for it, and it's got loads of resources. And then beyond, I know it's a long way to travel, but it's not so long if you've got faster propulsion, and then you've got, with gravity assist from Jupiter, you've also got, you're talking about years, not decades. And then if you're talking, and then there's Saturn's Titan, which is a wonderful place in ways. I think you need to look carefully at the planetary protection. Is there any native life? But it's extremely cold. The question really is whether there's native life that could survive in an Earth habitat. That seems unlikely, or whether Earth life could survive there in the cryovolcanoes, which are volcanoes that produce liquid water. But it's a wonderful place for human beings because you don't need spacesuits. The atmosphere there is 1.5 times, a bit more. It's denser than Earth atmosphere, and it's I can't remember the ratio, but it's a higher pressure. And this means a spacesuit, basically what a spacesuit does is it contains the pressure of the Earth's atmosphere. And it's not just a little container for oxygen. You need the pressure. You'll die without the pressure. And with Mars surface pressure, with scuba gear, you would die within seconds. You would go unconscious within seconds, because your lungs are not able to take up any oxygen from the atmosphere. Even the air in your lungs wouldn't work on Mars. If you were put on Mars and then without a spacesuit, then within a minute you'd be unconscious. You wouldn't be able to use the oxygen in your lungs. You can't take a deep breath. Though if you take a deep breath, then your lungs are just going to explode. It's not a good idea to take a deep breath and try and hold it because of the depressurization. And the reason is because at the temperature of our lungs, then the moisture that lines our lungs will immediately evaporate. It boils. The moisture lining our lungs boils. The moisture lining our tongues and our mouths boils. And the moisture on our eyes boil. But you wouldn't actually experience very much of this. You wouldn't experience boiling lungs. Not heat, but just evaporating, because water boils at a much lower temperature. Or, for instance, you can't get a good cup of tea on the top of Mount Everest because it reaches boiling point too soon. So it's the same with your lungs on Mars. It actually boils at well below blood temperature. And so you wouldn't be able to take a single breath. All the moisture would boil, none of the oxygen can be absorbed, and you just stay conscious for as long as you have oxygen in your blood, which isn't very long. There isn't very much oxygen in our blood. There's plenty in our lungs, but not much in our blood. So the Mars surface is no use for you can't breathe that, and so you need spacesuits. But the spacesuit is keeping the pressure, and without the pressure we can't breathe. But on Titan, then you already have this more than an atmosphere of pressure, so you don't need a spacesuit. And you could just manage with scuba gear. But this just ordinary scuba gear such as you use in the sea, with an oxygen mask, with an oxygen tank, and you'd be able to walk about on the surface of Titan. The only problem is the extreme cold. But the insulation works much better at colder temperatures. And you would use something not much different from a standard scuba gear wetsuit, with it's just a little bit thicker, but quite manageable. But I can't remember anything about that thick. And you'd certainly be able to walk around and be very flexible. Spacesuits are very, very unwieldy. They're just very stiff. Especially the gloves. It's described because you've got the pressure difference of an entire atmosphere. If you try and hold something in a spacesuit glove, then it's like having your fingers inside hose pipe, a garden hose pipe, and trying to bend it. It's almost impossible to bend. But on the Titan surface, you would have just ordinary gloves, but very thick insulation. You'd have just ordinary wetsuit. You would have heaters in your boots, and heaters in your other parts of your suit probably as well to keep you warm. And along with all this insulation, you'd have a scuba gear. You'd have a helmet, but not a pressurized helmet, just for the oxygen, and you'd be able to walk around on the surface of Titan. And that's a huge saving. It also means that the gear you use is very easy to make. You could actually it's no different from the gear you'd buy in a water sports shop, a diving shop. It's just everything a little bit thicker and some heating in your boots. that's what Titan. So Titan is one of the best places for surviving, and then you could have habitats which are just built as like great big huge tents, and you fill them with oxygen, and the pressure's the same inside and out, which makes it much easier construction. The winds there, the winds at ground level are gentler than gentlest breeze. Just gentle breezes, no possibility of any damage from wind. The ground is stable, you don't have earthquakes. There are very strong winds, kilometres or so up in the atmosphere, with a big difference in the wind velocity. So you could have floating turbines. The gravity is much less, it's similar to the moon. You could actually fly. Human beings could fly by flapping their wings in the Titan atmosphere. It's a really fun place. And I mean, it's nowhere near as good as Earth, because but it's better than almost anywhere else. And the wind can be used for power generation. So although there's hardly any light there, there's plenty of power available in the winds in the upper atmosphere. You'd have floating turbines. You can float a turbine, especially in those very light conditions. And the wind blowing through it is tethered, of course, and then the wind blowing through the with cables, and the wind blowing through it would generate all the power that you need for your colony. And so long as it's safe for the native Titan life, which we don't know. I don't think we should not send humans to Europa. We can send to Callisto, because Callisto doesn't have any connection. It does have underground seas, but they're so far below and completely disconnected with the surface, but it's just covered with these cratery things, and there's no way there's any connection between the surface. It's classified as category 2, just like the moon. So we can certainly send humans to Callisto. So I think this is a future that we have, and then we have humans on the moon, and you can build spaceships on the moon. The moon is an ideal place for building spaceships. The Earth is a stupid place to build spaceships, because your spaceships on the Earth, they have to get into orbit through the atmosphere, and you have to have a huge amount of mass to get of fuel, and a tiny bit of spaceship that gets into orbit. If you send a spaceship into orbit from the moon, then only about half of its mass needs to be fuel. It's far easier to get. So I think that our future, maybe 50 years from now, then all the spaceship factories will be on the moon. 50 to 100 years from now, they will be making them on the moon. Just about everything. I think everything you need to build a spaceship is on the moon. And so I think that's where we're going to be building our spaceships. I don't think Elon Musk will be building his spaceships on Earth in the late 21st century. I think he'll have a factory on the moon, and anyone else who's building spaceships. So anyway, some fun ideas for the future, and then the lunar caves are amazing for humans. They're absolutely huge. They're at least, they look as if they might be 100 meters long. Theoretically, in the lunar gravity, they could be up to several kilometers in diameter. We know that they're up to tens of meters in diameter. They could be much larger. And this talks about, you could have a cave there which could fill with air and use as a first colony. And that's as big as the biggest ones, as the really big ones in science fiction. You have entire cities in there below the surface. And then you can take materials from asteroids and convert the asteroids into these habitats. And then if you have these habitats, then these habitats, they can spin them for gravity very slowly. And I think for various reasons I've talked about in my book, that actually our spin tolerance is much higher. I don't want to go into all that. Our spin tolerance is much higher. But however we do it, there's enough material in just the asteroid belt alone to have habitats for 1,000 times the land area of Earth. And that's including all the radiation shielding, very thick radiation shielding that you need to protect people inside them. And then you can also have thin film mirrors which collect sunlight, and these are practical right out to beyond Pluto. You can have just free floating habitats orbiting around the sun independently, and out there of course you've got lots of ice and stuff, and you can build them right out to beyond Pluto with just using larger and larger mirrors to concentrate the sunlight. I talk about that in my book as well. I've got a section where I've got sites for all of this. These are not just eccentric ideas. I've got sites for this stuff in my books. So you can go and have a read about it, and I think you could get lots of fun ideas and loads and loads of stuff. We shouldn't just be focused on Mars. I don't think it should just be Mars, Mars, Mars. And some people think the Venus upper atmosphere has got a lot to offer as well. And I know that lots of people who say, oh, that's nonsense. But I think if you like the Venus upper atmosphere, depends on how troglodyte you are, or how much you like being, how much you like wide open vistas. If you like wide open vistas, it's very attractive because you're floating above the clouds, and you see. And I don't like claustrophobic. I'm rather claustrophobic. I'm not very much a cave dweller, but I would love living up on the top of the clouds. So for me, the Venus idea is rather attractive. But there's a possibility of life in the Venus clouds as well. Anyway, I talk about that in my book, and lots of other things. So yeah, I'll end by sharing my book. Here it is. So my Touch Mars. So as I say, it's free. I'll put a link in the URL description, and so you can go and have a read of that. And then it's got links to the moon articles below that, and so I find out a lot more about all this stuff. And then we've got my Touch Mars Facebook group and the Case for Moon First Facebook group, so I'll give links to that as well. There's of course the virtual astrobiology group if you're interested in astrobiology on Facebook, and I give a heads up for them. It's a good place to talk about anything to do with astrobiology. And that's it. That's it. I hope you enjoyed this, and now I will finally stop. And if you've got this far, then you must have enjoyed the talk, and thank you for listening.